Welcome back. As discussed in the previous video, Java variables or primitive types must contain appropriate primitive type values. The values can be literal, hard-coded, or computed. Java allows us to define literals using different bases. In this video, we will talk about various types to specify literal types for literal values for primitive types. For integer literals, we can use a number of different bases to specify literal values. We can use base 2, base 8, or base 16. And there's a corresponding prefix we can use. For floating point literals, we use a prefix to indicate whether we want to use float, single precision, or double precision. And note that the default is actually double. If you simply type 3.14 in your code, in your program, it's assumed to be a double. Now let's look at an example. As usual, please pause the video and write down your answer before we continue with our discussions. Welcome back. Let's try this example. If you run this program and run it again after you comment out each test cases, and you'll notice that all three representations or literals are stored as the same quantity. When you print out, they look the same, so the external representation is the same. This two binary string method defined in the integer class allows us to see the underlying bit pattern or the internal representation of the quantity, and you'll see that they all look the same. So what that means is we can specify the quantity in different bases, but internally, if they're the same quantity, then internally the representation or the bit pattern is the same. So now let's go back and look at another example. So please pause this video and write down your answer before we discuss. Welcome back. Let's check out this example. Okay, in this example, we're experimenting with floating point numbers, floating point literals. Let's run the program first. Well, this shows that we have a floating point number, a literal, and we can assign it to a variable and we can print it out with a limited number of digits, or we can, if we want, we can use this trick to print out all the digits that are significant. So as you can see, we have a pretty good amount of precision, a lot of digits, using just the floating point number. Okay, now let's switch to another case. So what if we add more digits to our literal? And as you can see, the numbers on the screen in the console, they don't seem to change. What that indicates is we can add as many digits as we want, but floating point representation or floating point type has a fixed precision. Remember that there are limited number of bits we can use to represent floating point numbers. So at a certain point, Java will have to truncate the bits or the digits, so we don't get high precision by just adding more digits. But however, what we can do is to switch to a more precise representation, the double precision, which use twice as many bits to represent a quantity of this type. So I'm going to run this again. It's the same number, but we are using D, which indicates this. We intend to store this as a double precision floating point number. Okay, now the result looks very different. It's we see more precision, and that's exactly what we wanted. So, but keep in mind that neither representation, single precision or double precision, neither of them can give us absolute precise representation of quantities. So the root cause is the fact that there's a limited number of bits to store all the information, and eventually we'll have to truncate or lose bits, which result in loss in precision. We'll discuss how such issue can cause a problem, how a very small amount of error or imprecision in our number representation can get accumulated and become observable numerical errors in the next video.